All right, last couple of times, we've been going over the contributions to delta G of binding, both the enthalpic contributions, the sticking contributions, and also the entropic contributions. We saw that a lot of the enthalpic contributions can be very strong, but they're usually traded off with water. Stuff binds to water just as well as it does to each other a lot of the time, and so they end up being net not that strong. We talked about the van der Waals interaction, which is universal and always present, but again, also true for water. We talked about the strain energy. We'll talk a bit more about that either this time or next time, which is the energy required to deform the molecule when it binds. Sometimes when two molecules come together, they change their shape, and that costs energy. And then for the entropic contributions, we talked about the hydrophobic effect. We've talked a lot about the hydrophobic effect because it plays a very important role. It's the main source of actual sticking energy for the formation of protein, the folding of proteins in the first place, the formation of DNA molecules, and the binding of proteins to each other, proteins to DNA, and so on. We talked about the fact that water can be released, and every water molecule contributes quite a bit to the entropy, and it's favorable for binding, right? Because it's an extra degree of freedom that's being generated upon binding. That, of course, has to be balanced against the translational, rotational, and configurational changes, which, as far as I'm aware, are always unfavorable for binding. You might be able to imagine some situation where, especially the configurational change, might end up being favorable. I don't know, but all the cases I know of, it's always unfavorable. But all that has to do with the strength of binding so far, anyway. Now it's time to talk about, in Chapter 13, it's time to talk about the selectivity of binding. The main issue here, it isn't such an issue in other areas of chemistry, but in biological chemistry, if a protein molecule is going to bind to its binding partner, it has to do so in the presence of an enormous number of thousands of other possible binding partners. And that means selectivity is really important. If you want this red guy to bind to that orange guy and not to anything else, then the red guy can't stick to anything else. The orange guy can't stick to anything else, or at least nothing else that you don't want it to. And so how does that happen? We want to understand how the selectivity comes about and what we can do to predict it and understand it. All right, so here's a few few areas where selectivity is really important. If you've got some kind of signaling molecule, hormone, it better not bind to the wrong receptor. If it binds to the wrong receptor, it'll signal the wrong thing. It'll start the wrong process going off. That's going to likely kill any organism that has that happen. The same thing for DNA, a transcription factor comes along, and that's going to be the start of a transcription process, which is going to produce an mRNA, which is going to produce a protein eventually. You don't want that going on uncontrolled. You got to be able to control that, so you only want the transcription factor to bind at the right place, and you don't want it to bind at the right time. It has to be controlled, and you don't want it binding at the wrong place either. It has to bind at a transcription initiation site and not other places. Otherwise, it just gunks up the DNA. And here's an RNA protein complex of some kind, for example, binding to a ribosome in order to produce a protein. And again, you want that to bind to the right site and not to other sites on the mRNA, let's say. So it's not just the delta G of binding that matters. It's the delta G of binding to the true target versus the delta G's of binding to everything else. Everything probably sticks to everything else a little bit, but you've got to control which one it really sticks hard to and how much and which ones it sticks to just a little bit. The key to this, as I've said in the past already, is pattern matching. There's patterns of things that lead to binding, and when those patterns match, the binding is strong. When those patterns don't match, the binding is weaker. And also what other textbooks sometimes call the lock and key relationship. That basically means the shape of the molecules in question. We'll talk about that also. Let me emphasize something that will come up as we're going along, and that is that with these pattern matching contributions, the net delta G is often unfavorable. In other words, they stop or tend to reduce the strength of binding rather than increasing the strength of binding. But they can still contribute enormously to selectivity. If they're more unfavorable for all the false targets, then even if they're still unfavorable for the true target, they contribute to selectivity. All right, so the situation we're thinking about now is not just one binding reaction, but many possible binding reactions all going on at once. So the ligand can bind to a receptor, which we'll call R0, and we consider that one, just by convention, to be the true target. So R0 is the thing we want it to bind to, or it's supposed to bind to. But L can also bind to a whole bunch of other things. We call all those R1 through however many there are. And each of these binding reactions has a KD. The KD is, remember, a small KD corresponds to strong binding, and a large KD corresponds to weak binding. So all these KDs, presumably, for all the false targets, have to be larger and therefore represent weaker binding than to the true KD. That pretty much has to be true, right? Unless there's an enormous excess of this true target, the only way you're going to get binding to the true target but not the others is if the KD is stronger for the true target than for the others. I guess there probably could be an exception to that, again, if there's an awful lot of excess true target over all the false targets, but that usually isn't the case. In fact, usually it's the other way around. There's more false targets than true targets, and in that case even more so, the KD for binding to the true target has to be stronger and weaker for all the others, and that's where the pattern matching comes in. All right, so the true receptor competes against all the others for the L. And what can happen, apart from any false signals or anything else, one of the other things that can happen is that all these false targets, if they bind too much, even if they don't individually bind very much, if they all bind a little bit, they can still suck up all the L that's present and basically deny any L to the true target. Basically, they just absorb all the L, and that can be bad too. The first thing we want to look at is the fact that this whole idea of specificity, I've been speaking so far as if specificity were a fixed property of L and R0, let's say, but that isn't true. It depends on the concentration of L and R0. So let's see why that's so. Let's suppose that we have a KD for R0, the true target, and then there's one other false target, which we'll call R1, and we have a KD for that. The KD for the true target is smaller than the KD for the false target. And that means that if the L concentration is really low, like it is here, so the L's in this case are the little blue dots. The true target are the red dots. If we have the L concentration smaller than the KD for the false target, but larger than the KD for the true target, then you're going to get binding primarily to the true target. On the other hand, if you start to raise the L concentration, so now the L concentration is larger than the KD for the true target, but it's on the same order of magnitude or starting to approach the value of the KD for the false target, now you're going to start getting a lot of false targets binding too, right? And that's bad. Usually you want things to just bind or almost only bind to the true target. And then, of course, you can keep raising L and get to the extreme situation where it's greater than both KDs, And in that case, both the false target and the true target will get saturated. So whether you get specificity of the sort that you need or not depends on the concentration of L that's present in the cell or in the environment or whatever. And so specificity depends on concentration. A thing that's good, a setup that's good and gives you the proper specificity at one concentration, let's say 1 micromolar of L, won't give you the right specificity at much higher concentrations of L, and won't give you enough binding to the correct target if it's much smaller than that, right? So there's a range of L's over which the specificity is what you want. It is possible to quantify those ideas to a certain extent. We're going to define now a quantity called alpha, which we will call the specificity. What is that quantity? Well, it's just the ratio of all the L that's out there, which is bound to the true target receptor, to the ratio of L that's out there that's bound to the false target. So when alpha is big, that means there's a lot more L bound to the true target than there is to the false target. When L is starting to get small, then these two have equivalent amounts of L bound to them, and if it gets much less than 1, then stuff's binding to the false targets and really not binding to the true target, which is, of course, the opposite of usually of what you want. How do we go about using that idea? Well, if alpha is the ratio of true to false, then it's the ratio of the concentration of L that's bound to the true target to the L that's bound to everything else, the false targets. We can just rewrite as concentration of R0L over the sum of all the concentrations to all the other possible false targets. Then we can use the fact that we know what the binding fraction is between any two proteins. It's equal to 1 over 1 plus the Kd for binding between the pair in question, divided by the L concentration. And now if we multiply this by the total amount of R0 that's present, then the R0 times the fraction that's bound, that's just R0L, right? And over here on this side, we're multiplying also, so we get R0 total. And that gives us the expression that's down here. It gives us the total amount of R0 bound to L, that is the numerator of our expression up here, in terms of the concentration of L and the Kd between the two. And we can do that, of course, also for all the false targets, and that if we do that and plug all those expressions up in here, then we get our final expression, which is rather complicated, and we'll never use this really in any complicated case, but it's valuable in simple cases. That gives us the ratio of true to false binding as a function of the L concentration. And so the fact that specificity depends on L is now given explicitly in terms of the concentrations of each of the targets, the KDs for each of the targets, and the concentration of our ligand L. Let's consider a simple case, the simplest case possible, where there's just one false target and one true target. In that case, this denominator down here, the sum just has one term, and our alpha expression becomes this, right? Just one term down here. And to simplify things even more, let's suppose that the total amount of the true target is equal to the total amount of the false target. So you've got equal amounts of both true and false targets, and there's only one false target. So this is really the simplest of all cases. If you want to consider all the more complicated cases, you can, but it's always best to understand the simple cases first. If you do that, then this concentration and this concentration divide out, and another step of algebra gives you this expression down here, actually, which is the same as the one up here. Gives the alpha, the ratio of true to false, in terms of the false Kd divided by L and the true KD divided by L. And now if you plot this value, this ratio, as a function of the log of the L concentration. Why the log? Well, because we want a lot of range of L. We're going to vary L from 10 to the minus 10, a tenth of a nanomolar, up to 10 to the minus 6, a micromolar, so that's 4 orders of magnitude, so we want to use a log scale. We're going to plot it. We're going to plot this selectivity ratio, or selectivity, as a function basically of of the L concentration, or the log of the L concentration, for two different cases. The first case is when the ratio of the KD for the true target to the ratio of the KD for the false target is 1 over 100. In other words, the binding to the true target is 100 times stronger than the binding to the false target. And furthermore, to make things just a little bit more concrete, we're going to say that the KD for the true target is 10 to the minus 9, so nanomolar affinity. And therefore, since this guy is 100 times smaller, 100 times tighter binding than the other guy, the KD for the false target has to be 10 to the minus 7. That's this purple curve or pink curve, whatever you want to call it, the top curve, as a function of L. So this curve, if I'm at very low L concentration, then I get an alpha of 100. That's, of course, reflecting the fact that the KD for binding is 100 times stronger for the target, for the correct target, and the fact that now there's almost no L around, and so all the L is being grabbed by the correct target, none of the false targets being got any L on it at all. And in that case, you're going to get 100 times more of the true target than the false target. So that makes sense. But if that's the case, you've got a situation like this where you're getting almost no binding. So the red guy here is the true target, the gray guy here is the false one. You're getting a little bit of binding, just, if you're not quite at zero, but you're at very low concentration, then you're going to get a tiny bit of binding to the true target and no binding to the false target. That gives you a great alpha, but you usually want to get better saturation of the true target, right? You've got no saturation, low saturation of the true target. What you really want is saturation of the true target and selectivity at the same time. So if we start increasing the concentration of L, our selectivity starts to drop down, because now we're going to get occasionally a binding to the false target, but we're going to start saturating our true targets much better. And so something like this, where we're at sort of halfway down the scale of alpha, possible alphas, an alpha of around 50 here, is probably about the ideal situation for most processes in biology. But, and then if we keep going down, if we keep raising the log L concentration after that, well, we're going to saturate, our true target even better, of course, but now we're going to start saturating the false target too, so we're losing our selectivity. All right, that's the case when there's a 100-fold advantage for the true target over the false one. But what if you've only got about a 10-to-1 average? Well, it's the same story more or less, except your selectivity, of course, can never be quite as high. Here we had 100-to-1 selectivity. Here we've only got 10-to-1 selectivity because our KD ratio isn't so great. And furthermore, in order to get some saturation, we've got to come down here someplace, which means our effective practical selectivity is going to be a lot smaller still. So you probably want selectivity that's more in this range than in this range in order to get good results. All right, here's another chart that shows basically the same thing, a little bit, maybe even a little bit clearer. Again, just one true target and one false target. And here again a ratio of 100, but the KD for the true target is 10 to the minus 8, and the KD for the false target is 10 to the minus 6. And now we're again plotting the log of the ligand concentration down here, and plotting two different things on the y-axis, the specificity ratio on this y-axis, and the fractional occupancy, or our saturation, if you like, on the other axis. And so this curve is showing the specificity, and these two curves are showing the fractional occupation of both the true target and the false target. So this fractional specificity out here is pretty good, as you can possibly make it, but we're only saturating, a tiny amount, probably about 10% of our true target. As we come down in come up in concentration, we come down in specificity, we've lost about half our specificity here. It's only 5 now. But the occupancy is now much better. We've got 50% occupancy or so. That's a better signal, right? A better switch, or a better action in any case. And if we keep going up in concentration, eventually we saturate out the true target, but we're now starting to bind significantly, starting to saturate the false target as well. And if we keep raising the concentration, eventually we get, of course, to the point where we're saturating both of them. All right. So that's sort of the mechanics, if you like, of the binding process. And that describes the selectivity process nicely. But what we'd really like to know next is what molecular features give rise to selectivity. What kinds of things are we looking for on a protein or a DNA, or a small molecule for that matter, that give rise to selectivity? And we're going to spend the rest of the time, I think, today and also next time, talking about what all these features are. There's a fair number of features, and it's a rather complicated thing. And you can't always tell just by looking at two molecules whether they bind tightly or whether they bind specifically or not. But after the fact, when you know that they do bind selectively, let's say, oftentimes you can rationalize and understand why that's true. Actually predicting ahead of time that two molecules bind strongly and specifically is kind of at the very, very edge of what it's possible to do with molecular simulations these days. Sometimes you can do it accurately, and probably more often than not you can't. All right, so let's look at the molecular features. First of all, there has to be sufficient binding strength. You have to have enough binding strength so that at whatever the ligand concentration is, if it's 1 nanomolar, for example, then you've got to have a KD of 10 to the minus 9 in order to get even sufficient binding strength to bind anything at all, for the target to bind anything at all. On the other hand, if you have more than you need, if you made this, let's suppose you have 1 nanomolar L typically in a cell, and you decide, let's do a really good job and make a KD of 10 to the minus 12, so now it's 1,000 times stronger than it needs to be to bind the L. The problem with that is you can never get the L back off again, for one thing, but another thing is that when the binding strengths get strong like that, they tend to start binding everything. And so you start to get indiscriminate binding, you start losing specificity, yeah. There are contributions to delta G, so this is the old strength issue that we've been talking about already, and the contributions, to put them in 4 nice categories, are the H bonding contribution, the electrostatic contribution, the strain contribution, and the hydrophobic effect contribution. There are, of course, also the other entropic contributions up here, these guys, and they contribute to the strength, but they don't contribute to the specificity because they're always present, so, or at least not so much. So these are the 4 that we're going to mostly talk about. Then you're going to match patterns, and the patterns that are going to match are the molecular shape, first of all, because you can't really get a nice interface of interaction between two molecules if they don't fit with each other, so molecular shape is kind of the beginnings of things. And that's especially true for larger molecules. For smaller molecules, especially if you've got a smaller molecule binding to a bigger molecule, well, the molecular shape isn't so important. There's got to be a pocket of some kind, but it doesn't have to match the shape of the molecule too closely. It just has to be big enough to fit the molecule. Then there's a pattern of H bonds on the surface that has to match the donor and acceptor pattern of H bonders on the other molecule, on the ligand. The electrostatic potential pattern on the two molecules has to be complementary, right? Wherever there's a plus on one surface, there's got to be a minus on the other and vice versa. And all of these contribute to specificity. Then there's the last one, the hydrophobic patches. That's the hydrophobic effect. So there's a patch on the surface that's a little hydrophobic. That means, and you've got another molecule which also has a hydrophobic patch. Those two hydrophobic patches will stick to each other. But usually this contributes greatly to the strength of binding, but usually doesn't contribute as much to the pattern matching, to the specificity of binding. So a common way in which molecules bind strongly enough to get to bind their target at all, and also specifically enough so they don't bind everything else, is to use the hydrophobic effect to make a core of binding that gives you the strength that you need, and then use H bonding, electrostatics, and shape matching to give you the specificity. And yeah, that's just shown here. There's not too much more to say. Here's the hydrophobic core that's coming together. Notice that at least in this picture, the hydrophobic core isn't real huge. It doesn't have to be real huge. The hydrophobic effect is strong enough so that even a few residues are enough to contribute to make quite a strong binding. And then there's something else, hydrogen bonding or electrostatics, which have a complementary pattern on each surface, right? For hydrogen bonding, wherever there's a donor on one surface, there has to be an acceptor on the other and vice versa. And for electrostatics, wherever there's a plus on one surface, there has to be a minus on the other, and so on. Yes, and I put these little arrows in here as well to indicate that when they come together, there is also a contribution from water release. Okay, so yes, here's the idea. Here's, for example, number B here. Looking at the patterns, you can see the hydrophobic effect patterns match. That's less important. Even if they didn't match, you'd probably get some good binding because all they have to really do is overlap. The hydrophobic effect will still be strong. But notice that the pattern of blues and greens here, whatever those are, they could be H-bond donors and acceptors, they could be plus and minus charges, also are complementary. Wherever there's a red here, there's a blue here, and vice versa. And likewise, this pair has the same property, matched hydrophobic effect patch and complementary in the other patterns. All right, let's look at one quite simple example of how that works in a real case. This is the SH2 domain. It's an important domain for sensing, for signaling systems that lead to proliferation and many other cell properties or cell processes. And if one of the main reasons why these switches have been studied really extensively, practically to death, for many decades, well, maybe not many decades, but at least for 3 or 4 decades now, yeah, maybe 3 decades, is that one of the switches they control is cell proliferation, which determines whether a cell goes cancerous or not, right? If a cell is in your body, grows to make a muscle tissue or a stomach lining tissue or something like that, and then for some reason decides to start growing on its own and not behave itself, then yeah, you get a big tumor, which is bad, bad, bad. All right. In this case, what the SH2 does is bind to tyrosine or phosphorylated tyrosines like this, phosphotyrosines. That's because the phosphor group on the tyrosine is a signal that's used for turning cell processes on and off for a whole lot of different processes, but cell proliferation among them. And the question is, how does the SH2 domain here recognize this phosphotyrosine? And if we look at what it's doing, here's the binding pocket for a peptide that's got a phosphorylated tyrosine on it. That's kind of buried down in here. There's the actual phosphate group. And you can see that the binding pocket does indeed, it's a little invagination in the surface that allows the peptide to come in and so on, and then there's a deeper hole that allows the phosphotyrosine to get in even a little further. But the shape isn't really the important thing here because this is a flexible molecule. It can accommodate itself to quite a few shapes. All that really has to happen is that there be a binding pocket that's not actually repulsive and big enough to accommodate what we're trying to bind to. But look what happens on the interior, down inside here. There's the phosphate group right there. That guy right there is this phosphate group. And the rest of this is the rest of the tyrosine here. All of this. And look what kind of pattern there is on the SH2 domain. There's a hydrogen bond to the phosphate group there. There's a hydrogen bond to the phosphate group there. There's another one there and another one there. And there's another one too that I'm missing someplace. There's 5 of them anyway. Yeah, did I count them? 1, 2, 3, 4. Where's the 5th one? That one doesn't count because it's not to the phosphate. It's between 2 residues on the same protein. Anyway, I can't find the 5th one, but there is a 5th one. So there's 5 hydrogen bonds, and in order to bind really tightly, all of those guys have to be satisfied. It's really unlikely that something other than a phosphotyrosine is going to come along and fit that pattern of hydrogen bonds well enough to get, let's say, nanomolar binding. Anything else that comes along either isn't going to fit in the pocket at all, or it's going to fit in there, but it's not going to have the right shape and properties to match that hydrogen bonding network. And so the SH2 domain is very specific for those kinds of residues. And that's what this says too. Accidental matching is very unlikely. We can go a little bit further with that by putting some numbers on all these things. Let's consider a case where I have one receptor that's the true target, and again, just one false target receptor. And let's just put some delta G values to the various contributions that would lead to binding. Let's suppose that both of these guys have equal amounts of hydrophobic effect binding. So minus 50 kilojoules per mole. That's a pretty big binding effect. From the hydrophobic effect for both of them, let's suppose there's a hydrophobic patch on this one, there's a hydrophobic patch on that one, and the target ligand also has a hydrophobic patch. So as far as the hydrophobic effect itself is concerned, alone is concerned, it would bind equally well to both of them, and very strongly, in fact, too. But then there's an electrostatic contribution that's unfavorable to binding, but it's only plus 20 on the true ligand, on the true target, but it's plus 40 on the false target. In other words, they're both unfavorable, but the false target is more unfavorable. And then, likewise, for the hydrogen bonding, it's net 0 for the true target and net unfavorable by plus 10 on the false target. And the net result is that there's 50 kilojoules per mole of unfavorable interactions on the false target and 20 kilojoules per mole of unfavorable interactions on the true target, which means that when things get all added up over here, the true target has an advantage of minus 30 kilojoules per mole. So these pattern matching interactions are actually unfavorable. They actually hurt the binding, but they help the specificity. And minus 30 kilojoules per mole is a pretty good pretty good binding. If you put that into our formula for the KD, e to the delta G bind over RT, you get a KD of 10 to the minus 6 for the true target, and a KD of 1 for the false target, which means that this particular pair would have, well, the true target would have an advantage of almost 1,000,000-fold, 600,000-fold over the 160,000-fold actually over the false target. So in practice, this means that, of course, you would saturate out this true target long before, at small concentrations, at micromolar concentrations, and it would take something like 1 molar concentration before you started saturating out the false target. So the false target just wouldn't be even relevant in this case. And so the lessons here from this little example are, first of all, that a relatively modest difference or advantage on the part of the true target, 30 kilojoules per mole is not a huge amount, can give you a huge advantage in the actual binding. That's one lesson. The other lesson is that the pattern matching interactions don't have to be favorable in order to still provide specificity. As far as the strength of binding contribution from HPE is concerned here, they're both the same. It's these unfavorable contributions from the pattern matching that allows the ligand and the receptor to recognize each other even in the presence of the false target. All right, with that, let's see. I think I talked about this before. Yes, I think I'll stop here, and we'll talk next about a rather extended and detailed example of how specificity works and how recognition occurs for DNA and protein interactions specifically, which is a very important class of interaction.